Right now, signals from Voyager 1 reach Earth with less power than a single atom's vibration. So faint, we should be drowning in cosmic noise. Yet we see photos from across billions of miles. If this invisible lifeline fails, our visions of distant worlds vanish. How do we decode these impossible whispers from the edge of the solar system? And why does a scratched DVD hold an unlikely clue? 15 billion miles from Earth, Voyager 1's radio signal is so faint that by the time it arrives, it carries less energy than a single snowflake landing on your palm. The numbers almost defy belief. A 23-watt transmitter, weaker than most light bulbs, sends a signal that shrinks to just 1/10,000th of a trillionth of a watt at Earth. That's a whisper lost in the roar of cosmic background radiation. The farther a spacecraft travels, the more its signal spreads out, thinning across space until it's buried by static and noise. The free space path loss for Voyager is over 293 decibels, an unimaginable drop. If we tried to bridge that gap without help, we'd need a transmitter the size of a city and a receiver dish bigger than a football stadium. Yet somehow, from this impossible distance, we receive crisp images and streams of data. The challenge isn't just distance, but the relentless weakening of every bit of information as it crosses the void. Irving Reed, working at MIT Lincoln Laboratory in 1960, set out to solve the problem of lost information in noisy channels. Alongside Gustav Solomon, he designed a code that treats each chunk of data as a point on a mathematical curve, a polynomial. By adding just 32 extra bytes to every 223 bytes of real data, Reed-Solomon codes allow a receiver to reconstruct the original message, even if up to 16 bytes are damaged or missing. That's a 14% overhead, small but powerful. The decoder uses the extra information to pinpoint and repair errors, like solving a puzzle where some pieces are missing. This same approach keeps scratched DVDs playing without skips, and it is what lets NASA recover images from spacecraft battered by cosmic rays. On missions like Cassini, Reed-Solomon coding preserved 1 billion bits of Saturn ring data, correcting errors that would have left entire images unreadable. The math became a shield, turning fragile signals into reliable stories from the edge of our solar system. At the heart of Earth's connection to the cosmos stand 3 enormous antenna complexes, each crowned by a 70-meter dish, structures taller than a 20-story building and weighing nearly 3,000 tons. These deep space network giants are so sensitive, they can catch a signal from a spacecraft on the far side of Saturn, even when the transmission is weaker than a single snowflake's impact. To pull off this feat, engineers chill the receivers with liquid helium to just 3 degrees above absolute zero, squeezing every last bit of noise out of the system. During the Cassini mission, these antennas captured 1 billion bits of Saturn's ring data, each one sent across over 1 billion kilometers and battered by cosmic interference. Even when the signal dipped below the background hiss of the universe, the network's hardware and error correction worked together to reconstruct every detail. The result? Crisp, uninterrupted images and science, beamed home from the edge of the solar system. In 1993, the world of coding theory was jolted by the work of Claude Barreau and Alain Glaveux. Their invention, turbo codes, shattered expectations by pushing data transmission rates to within half a decibel of the theoretical Shannon limit, a boundary once thought unreachable. Suddenly, spacecraft could send far more information with the same faint signal. When NASA's Spirit and Opportunity rovers landed on Mars in 2004, turbo codes let them beam images back at 128 kilobits per second, a tenfold leap over previous missions. The Mars Reconnaissance Orbiter took this further, using a turbo code with a rate of 1/6, meaning 6 bits were sent for every bit of real data. This brute force redundancy allowed the orbiter to transmit sharp images of Mars' surface from 140 million miles away, revealing details just a meter across. The James Webb Space Telescope, stationed 1 million miles from Earth, relies on LDPC codes, built around sparse matrices, to send 28 megabits per second, enough to download a 65 gigabyte image in 6 hours. Even missions like Rosetta and InSight, facing solar storms and cosmic static, use these modern codes to deliver science data from the edge of the solar system. Error correction was no longer just a shield. It was now a software engine driving a revolution in deep space communication. On February 18th, 2021, the first raw sounds from Mars traveled 293 million miles to Earth, a 60-second audio clip packed with atmospheric rumbles and the faint whir of Perseverance's machinery. Along the way, cosmic rays and solar storms scrambled over 2,000 bits in the audio data. But as the signal reached NASA's Deep Space Network, an array of 70-meter antennas locked on, combining their strength to pull every last whisper from the noise. The LDPC error correction code went to work, repairing every single flipped bit in real time. Not a pop, not a click, not a single gap survived the journey. The final recording arrived flawless, an unbroken thread from Martian wind to human ear. Phase shift. Keying encodes each bit as a unique twist in the radio wave, making the signal more resistant to background noise and interference. Next, the convolutional encoder transforms every bit into a sequence of overlapping outputs, effectively duplicating the information so that even if some bits are lost, the original can be pieced back together. Interleaving then shuffles the data, spreading any burst of errors caused by cosmic rays across the stream, so they appear as isolated glitches instead of clusters that overwhelm the correction process. Every image from deep space proves this. With the right code, even the faintest signal survives. As our reach grows, error correction remains the invisible bridge between us and the unknown.